In the emerald depths of Verdantia, where trees tower like living skyscrapers and the air hums with bioluminescent conversations, there exists a class of creatures so monumental that they don't just inhabit their environment, they shape it, they mold it, they engineer it on a continental scale. These are the Megapoda, Verdantia's giant land dwellers, and their story is not just one of survival, but of deliberate, conscious creation. From the armored Rhino-Turtles cultivating living gardens on their backs, to the tunnel badgers whose excavations create entire underground civilizations, to the mysterious cloud makers whose very breath influences global climate, these are not mere animals. They are ecosystem architects. They are landscape artists working on geological timescales. They are the reason Verdantia's ecology doesn't just function, it flourishes with a complexity that makes Earth's most diverse ecosystems seem simple by comparison. Today, we descend from the canopy's glowing mysteries to the solid ground below, where gravity is 1.8 times Earth's pull, where every step requires immense strength, and where life has responded not with fragility, but with monumental resilience. Welcome to the world of the Megapoda, the giants who carry Verdantia's future on their backs, in their tunnels, and in their very bones.
Our first subject emerges from the morning mist like a mountain deciding to take a walk. The Rhino-Turtle, a name that barely captures its majesty. 4 to 6 meters long, 3 meters tall at the shoulder, weighing upwards of 8 metric tons. But its size is the least remarkable thing about it. Observe the shell. Not a rigid carapace like Earth's turtles, but a living, shifting landscape of interlocking plates. Each plate, some as large as banquet tables, is made of a unique composite, layers of silica-reinforced keratin over living bone, infused with vascular channels that allow controlled movement. The plates can rise, fall, shift, and lock together via hydraulic pressure generated by specialized heart-like organs beneath them. When threatened, the Rhino-Turtle doesn't just withdraw, it transforms. Plates rise to create razor-sharp ridges. Smaller interlocking plates slide into place, creating a near-perfect seal. Specialized glands secrete a quick hardening resin that bonds the edges together. The creature becomes an impregnable fortress. But this fortress has a secret. It's also a garden. Each plate cultivates its own miniature ecosystem, moss species that fix nitrogen from the air, symbiotic fungi that break down waste products, insect analogs that aerate the soil-like accumulations, even flowering plants whose roots penetrate microscopic channels in the plate itself. The Rhino-Turtle doesn't just carry these gardens, it tends them. See here, this rear claw, often mistaken for a defensive spur, is actually a precision gardening tool. The turtle carefully trims an overgrowing moss, then places the cuttings in a specific depression where they'll decompose and feed a particular fungus. This isn't instinctive grooming, this is cultivation. Each garden is unique to its turtle, reflecting age, travel history, and even individual preference. Scientist interview cutaway. Dr. Alara Vance, xenobiologist. We've tracked individual Rhino-Turtles for decades, and their gardens evolve. A young turtle might have simple moss colonies. As it travels, it acquires new species. We've documented turtles that deliberately seek out particular plants when they enter new regions. They're not passive carriers, they're active collectors, curators of botanical diversity. But why? Why would a massive creature expend precious energy maintaining gardens on its back? The answer lies in Verdantia's unique ecology. The gardens provide multiple services. They offer camouflage, the pattern and coloration shift as gardens grow and change, matching regional vegetation. They process waste. The turtle's urea and other nitrogenous wastes are absorbed by the plants. They regulate temperature. Evaporative cooling from the moist gardens helps dissipate heat in a world with twin suns. And perhaps most remarkably, they communicate. Certain plants in the gardens bloom only in specific emotional or physiological states. When the turtle is stressed, anxiety moss releases calming pheromones. When ready to mate, courtship orchids bloom with specific scents. When ill, medicinal fungi produce antibiotic compounds that the turtle absorbs through its shell. The garden is an externalized physiological display, a living mood ring on a monumental scale. Watch this social interaction. These two males aren't fighting, they're having a conversation. Their gardens are reacting to each other's chemical signatures. Mosses on one darken in a specific pattern. Fungi on the other pulse with bioluminescence. Flowers orient toward the other turtle. They're exchanging information about territory, health, even personal history. After 20 minutes of this silent botanical dialogue, they peacefully go their separate ways. Reproduction reveals even more sophistication. Rhino-turtles mate for life, a necessity given their 200-year lifespans. But here's the extraordinary part. Offspring inherit not just genes, but gardens. The mother turtle deliberately transplants cuttings from her own garden onto her eggs before burying them. When the hatchlings emerge, they already have starter gardens containing microbial and fungal symbionts crucial for health. They also inherit knowledge. The hatchlings instinctively recognize and prefer the plant species from their maternal garden. Scientists interview Cutaway. It's Lamarckian evolution meets cultural transmission. A turtle doesn't just pass on genes for a strong shell. It passes on the actual plants that will make that shell functional. It's like inheriting both the blueprint for a house and the actual furniture. Their movement through the landscape creates what ecologists call turtle trails, paths of enriched soil, dispersed seeds, and altered microclimates that persist for centuries. Where rhino turtles travel, biodiversity follows. They are, in the truest sense, gardeners of the continent.
While rhino turtles shape the surface world, another megapoda works in darkness. Meet the tunnel badgers, the engineers of Verdantia's underworld. 2 meters long, half a meter tall, with 6 powerful digging claws that can move 2 tons of soil per hour. But physical strength is just the beginning of their adaptations. The eyes are covered with transparent secondary eyelids that protect while allowing vision in loose soil. But they don't rely on sight underground. Those whiskers? Each is a multi-sensory array detecting vibrations, electrical fields, chemical gradients, and even quantum spin states of nearby particles. The nose contains more sensory neurons than a human brain. In absolute darkness, the tunnel badger perceives a rich world. It sees soil density variations as texture, hears root systems as singing structures, tastes mineral deposits as flavors, and detects the microscopic life in soil as shimmering clouds of activity. Its perception of underground space is more detailed than our perception of daylight landscapes. But why dig such elaborate tunnels? Early theories suggested simple burrows for shelter. The reality is far more magnificent. A single tunnel badger colony, usually 20 to 30 individuals across multiple generations, creates networks covering up to 50 square kilometers. These aren't random excavations. They're carefully engineered structures with specific purposes. Transport tunnels, wide, straight, with compacted floors for efficient travel. Ventilation shafts, vertical tubes creating convection currents that circulate air. Water management channels, sloped to direct groundwater flow with overflow chambers preventing flooding. Farming chambers, where they cultivate fungi on deliberately composted plant matter. Nurseries, temperature and humidity controlled via passive geothermal systems. Communication hubs, where vibrations transmit information across the network. Scientist interview cutaway, Dr. Eris Thorne, subterranean ecologist.
We've mapped these networks using ground-penetrating radar, and they're more complex than human subway systems. They display understanding of soil mechanics, hydrology, even basic aerodynamics. The badgers reinforce weak areas with deliberately mixed concrete of saliva, soil, and chewed plant fibers. They create drainage before digging living areas. This isn't instinct, it's engineering knowledge accumulated over generations. Their social structure reflects this engineering focus. Colonies have specialized roles: excavators with particularly strong forelimbs, architects who plan tunnel routes. Observations show them debating routes with head movements and vibrations before digging. Maintenance workers who constantly repair and improve existing tunnels, foragers who collect specific plants for fungal cultivation, and most intriguingly, teachers. Juveniles spend their first 2 years learning, not through trial and error, but through directed instruction. Adults demonstrate proper digging angles, reinforcement methods, ventilation calculations. The young practice on training walls of specially prepared soil. Knowledge is transmitted not just vertically from parents to offspring, but horizontally across the colony. An innovation discovered by one badger spreads to all within weeks through deliberate teaching. But the true ecological impact comes when tunnels are abandoned. When a colony moves on, which happens every 30 to 50 years as resources deplete, their abandoned network becomes the foundation for entirely new ecosystems. Plant roots follow the nutrient-rich tunnels. Small animals move in, adapting the spaces to their needs. Fungal networks colonize the walls. Water flows create underground streams. What was once a badger home becomes a multi-species subterranean city. Their relationship with other species is particularly fascinating. Tunnel badgers practice what we might call selective hospitality. Certain insect analogs are allowed to live in the tunnels as cleaning crews. Small lizard-like creatures are tolerated because they eat parasites. But plant-eating rodents are aggressively expelled. They might damage the structural roots that stabilize tunnels. The badgers recognize dozens of species and have different policies for each. A complex interspecies diplomacy conducted mostly through vibration patterns and chemical markers. Their communication system deserves special attention. By tapping specific sequences on tunnel walls, they can send complex messages across kilometers. We've decoded some of this tunnel code. Different rhythms indicate different urgency levels. Specific sequences convey information about food sources, predators, even abstract concepts like structural instability in Sector 7 or water table rising in the Eastern Network. Scientist interview cutaway, Dr. Eris Thorne, subterranean ecologist. Their communication has grammar. It has tenses. They can indicate whether something is happening now, happened recently, or will happen. They have spatial references more precise than our left and right. They use a three-dimensional coordinate system based on tunnel junctions. We're essentially looking at a tactile language. Perhaps most remarkably, tunnel badgers exhibit what we might call trans-generational project planning. A colony will begin digging a tunnel segment that won't be completed for 5 years, beyond the lifespan of the diggers. They leave detailed instructions in vibration patterns pressed into the walls at decision points. Future generations continue the project precisely according to plan. Some networks show evidence of century-long excavation projects with remarkable consistency of direction, slope, and reinforcement methods. In a very real sense, tunnel badgers don't just live in the landscape, they weave themselves into its fabric. Their tunnels become geological features that persist for millennia. Their excavations alter water tables, soil composition, and even surface vegetation patterns. They are silent sculptors working in earth and time.
From the depths we ascend, not to the surface, but above it, for among the Megapoda are those who have conquered not land, but sky. Meet the cloud makers, the living weather systems of Verdantia. To call them animals feels inadequate. To call them organisms seems restrictive.
Cloudmakers are atmospheric ecosystems in mobile form, 50 to 100 meters long, resembling nothing so much as living zeppelins made of translucent tissue, gas-filled bladders, and intricate internal structures that defy classification. Their basic structure: multiple gas bladders filled with hydrogen-methane mix produced by symbiotic bacteria, muscular sails that catch wind currents, a digestive system that filters microorganisms from the air, reproductive organs that release spores in coordinated atmospheric dances, and most remarkably, cloud-forming organs. Scientist interview cutaway. Dr. Lynn Park, atmospheric xenobiologist. Cloudmakers have specialized glands that release cloud condensation nuclei, tiny particles around which water vapor coalesces. But they don't just make clouds randomly, they make specific clouds for specific purposes. Different gland clusters produce nuclei of different sizes, leading to different cloud types with different effects. Observe this individual as it approaches a drought-starved region. It releases nuclei that create cumulus clouds, the puffy, rain-producing kind. Over 6 hours, it seeds a cloud bank that drifts over dry forest, releasing gentle rain. But why would a floating creature care about ground conditions? Because cloudmakers are deeply integrated into Verdantia's ecology. The rain they trigger promotes plant growth. Those plants release spores and pollen into the air. Those airborne nutrients become the cloudmaker's food. They're not just making rain, they're farming the atmosphere. Different cloudmaker families specialize in different weather patterns. Mistweavers create morning fog that reduces evaporation in vulnerable ecosystems. Stormcallers build thunderheads to break heat waves and harvest lightning energy. More on that shortly. Shadowcasters form high cirrus clouds that moderate temperature during peak sunlight. Frost preventers create insulating cloud blankets on cold nights. Their migration patterns are tied to seasonal needs. During the dry season, they congregate over drought-prone areas. During spore release seasons, they follow the aerial nutrient flows. During breeding season, they form massive floating colonies, thousands strong, their combined cloud-making creating temporary microclimates where their young can develop safely. Now, about that lightning. Cloudmakers don't just tolerate lightning, they attract it. Specialized organs on their undersides create massive electrical potential differences. When lightning strikes, conductive tissues channel the energy to storage organs filled with organic batteries. A single strike can power a cloudmaker for months. Scientist interview cutaway. They're essentially biological capacitors on a monumental scale. They store electrical energy not as ATP like our cells, but in specialized organelles that maintain charge separation almost indefinitely. They use this energy for everything from muscle movement to spore production to, we believe, some form of electrical communication we don't yet understand. Their reproductive strategy is equally extraordinary. When conditions are right, specific temperature, humidity, and electrical charge in the air, cloudmakers engage in atmospheric dances. They release glowing spores in patterns that create living constellations in the night sky. These patterns aren't random, they're complex displays of genetic fitness. The most beautiful, coordinated displays attract the most mates. The young develop in a remarkable way. Spores don't grow directly into adults, they form nursery clouds, small self-contained atmospheric ecosystems where juvenile cloudmakers develop over several years. These clouds are maintained by adults who adjust their composition, moisture, and temperature deliberately. It's akin to a bird building a nest, but the nest is a temporary climate system. Their impact on Verdantia's climate cannot be overstated. Computer models suggest that without cloudmakers, Verdantia would experience extreme temperature swings, irregular rainfall, and potentially catastrophic droughts in certain regions. They don't just live in the atmosphere, they maintain it. They're planetary climate regulators made of flesh and gas. But here's the most profound implication. Evidence suggests cloud makers are getting better at their job. Ancient fossils show simpler cloud makers with limited weather influence. Over millions of years, they've evolved more sophisticated cloud-forming abilities, more precise migration patterns, more efficient energy harvesting. They're not just adapting to climate, they're learning to manage it. And in doing so, they've become indispensable to Verdantia's ecological stability.
Individually, each Megapoda is extraordinary, but the true magic emerges in their interactions. For these giants don't exist in isolation. They form a collaborative network that shapes continents. Follow this chain of influence. A tunnel badger colony excavates near a hillside. Their tunnels alter groundwater flow. A spring emerges where none existed before. Rhino-turtles are attracted to the new water source. Their trails create paths for seeds to spread. Plants flourish. Their transpiration increases local humidity. Cloud makers detect the humidity gradient and seed clouds overhead. Rain falls. The new plants thrive. Their roots stabilize the soil, preventing erosion. The tunnel badger's excavations are now more stable. And so the cycle continues. They communicate across species in ways we're only beginning to understand. Rhino-turtles will sometimes deliberately collapse tunnel sections that threaten to undermine their favorite feeding grounds, but they always leave clear repair suggestions, specific arrangements of stones and compacted soil that show the badgers how to rebuild more stably. The badgers usually follow these suggestions. During drought, certain plants release specific volatile compounds. Cloud makers detect these thirst signals and prioritize rain over those areas. It's not a direct communication, but an ecological dialogue mediated through chemistry. Scientist interview cutaway, Dr. Silas Wren, macroecologist. We're seeing what looks like interspecies ecosystem management. The Megapoda aren't just responding to environmental conditions, they're collectively maintaining optimal conditions. When one group detects a problem outside their capacity to fix, they create conditions that attract another group whose specialty addresses that problem. It's a planetary-scale division of labor that's evolved over eons. Their movements create what we've termed ecological arteries. Rhino-turtle trails become seed dispersal corridors. Tunnel badger networks become underground waterways and root pathways. Cloud maker migrations become atmospheric nutrient transport systems. Together, they create a living infrastructure that connects ecosystems across thousands of kilometers. Perhaps most remarkably, they seem to have a form of transgenerational memory. Migration routes used today follow the same paths used for millions of years. But when climate shifts or geological events change landscapes, the routes adapt, and the new routes are remembered. How? Through a combination of genetic memory, cultural transmission, and physical modification of the landscape itself. A rhino-turtle trail, once established, persists for millennia, guiding future generations.
As we observe these magnificent creatures, we cannot help but reflect on our own relationship with Earth. The Megapoda offer not just biological wonders, but philosophical provocations. Where humans often see nature as something to dominate, the Megapoda see themselves as part of a system to maintain. Where human engineering often creates problems for later generations, Megapoda engineering creates foundations for future life. Where human agriculture often depletes, Megapoda cultivation enriches. Consider the rhino-turtle's garden, a perfect circular economy where waste becomes resource, where defense becomes habitat, where individuality becomes ecological contribution. Or the tunnel badger's excavations, creating not just homes for themselves, but infrastructure for entire ecosystems. Or the cloudmaker's weather management, not fighting climate, but working with it, guiding it towards stability. Scientist interview cutaway, Dr. Alara Vance. We came to Verdantia looking for alien life. What we found was alien wisdom. These creatures demonstrate that intelligence isn't just about problem solving.
It's about system maintenance. That success isn't just about individual survival, it's about contributing to something that outlasts you. In an age of human-caused climate change and mass extinction, their example isn't just interesting, it's urgently relevant. But there's a sobering realization here too. The Megapoda's way of life requires something humans struggle with: patience. Rhino-Turtle gardens take decades to mature. Tunnel badger networks span generations. Cloudmaker climate regulation operates on century timescales. Their intelligence is slow, deep, and profoundly long-term. Could humans learn such patience? Could we shift from short-term exploitation to long-term stewardship? The Megapoda don't offer easy answers, but they show us that such a way of being is possible, that life can be not just smart, but wise, not just successful, but sustainable across geological time.
As twilight descends on Verdantia, we observe the Megapoda in their evening rhythms. Rhino-turtles settling into wallows, their gardens glowing softly with bioluminescent fungi. Tunnel badgers completing the day's excavations, their vibration songs echoing through the earth. Cloud makers catching the last thermals, painting the sunset with deliberate cloud formations. They move with the certainty of beings who know their place in the world, not as conquerors, but as caretakers. Not as isolated individuals, but as interconnected nodes in a planetary system. Their strength isn't just in their size, but in their synergy. Their intelligence isn't just in their brains, but in their relationships. In human mythology, giants often represent primal forces, unthinking, destructive, something to be overcome. But Verdantia's giants tell a different story, of giants who build rather than destroy, who create rather than consume, who think in generations rather than seasons. The trails, the tunnels, the cloud patterns, these are more than biological phenomena. They are a language written across continents, a story told in soil shifts and rainfall patterns, a testament to what life can achieve when it thinks big, thinks long, and thinks connected. As we leave Verdantia's surface, returning to the stars from which we came, we carry with us not just data, but perspective. The Megapoda remind us that size can mean responsibility rather than domination, that engineering can mean nurturing rather than conquering, that success can be measured not in territory controlled, but in ecosystems enriched. They are the gentle giants, the patient architects, the silent gardeners of a world. And in their monumental, deliberate lives, they offer us a vision of what intelligence can be when it grows up. Not just smart enough to take, but wise enough to give back. Not just clever enough to survive, but visionary enough to thrive across millennia. This has been our exploration of the Megapoda. May their example guide us as we navigate our own planetary challenges. May we learn to think like giants, not in ego, but in responsibility, not in scale, but in stewardship.